Hi, everybody. Thanks for coming here. My name's Bennett Howard with Sodick Injection Molding Machines here, and Plus Tech is really the name of our side of the company. But thanks for joining us here. I want to thank the folks from Plastics Technology first and foremost. This has been a really fun show for us this year and past years. In particular, the Hot Shots competition is something that we've always enjoyed, and if you haven't already, go vote, go check it out. We were lucky enough to win it last year, and I know there's some really good parts in it this year. But yeah, I'm going to kind of describe here what we're running. I want to thank some of the partners that help us put together this cell first. First and foremost, Flowcon, a good molder here in Illinois. This is their tool that they built for their own needs, but allowed us to use it here for this demonstration today. We've got kind of a paint marker end cap that we're molding. And then the auxiliary equipment came from Matsui, another good partner of ours, so wanted to thank them as well. On the machine side, what we've got here is our GL100A press. It's a 110 US ton, so you can see fairly nice footprint for a 100-ton machine. And what we're running here, I don't know how close you can get, but a 4-cavity hot runner tool, just a polypropylene material. So nothing crazy in terms of materials. I know a lot of times we run an LCP or a PEEK or something like that to kind of showcase that. But what we're really trying to showcase here, I don't know how close you can get to that screen, but if you look at cushion, minimum cushion here, this is kind of what we like to show off here with Sodick. We'll go into the injection unit here in a second, but right now we're running at a 0.040 inch cushion, which equates to 1 millimeter cushion. So a lot of times people are afraid of a 1 millimeter cushion, particularly with the reciprocating screw style machine. But with the response time of a plunger, that acceleration, deceleration, we can minimize that cushion, but more importantly, we're also going to keep that cushion more stable. So if you look at the last consecutive 40 shots, we've got 0.000, so to a fourth decimal place in terms of cushion variation. And then also extremely stable fill time. But that's kind of the idea with Sodick is, you're eliminating some of these sources of variation, because of the injection unit design. So quickly, if you can follow me here. So when I talk about, response time and things like that and kind of how we've differentiated ourselves in the molding machinery world, it really comes down to this V-line injection unit. So, obviously it looks different. We've had some folks say, oh, is that a 2-shot machine? No, it is. We do have 2-shot machines, but it would be 2 versions of this. So what we've got here is essentially we're separating melting or material preparation from injection. So it kind of allows us to really control both a little bit further than you might on traditional molding equipment is the idea. So first and foremost, you're utilizing a stationary screw or really an extruder to kind of control that shear heat, right? Versus a back and forth kind of reciprocation movement, which could result in excess shear, maybe yellowing, burn spots, things of that sort. Now we're building one shot at a time, so material's being metered here, pushing the plunger back. Plunger hits a set point. This screw here stops turning and checks forward. We'll show you here on the next cycle. So once this plunger hits set point, screw stops turning, checks forward. So that's our shutoff, as compared to, you might be familiar with the floating check ring or a check valve in a traditional machine. So the idea is now we're shut off before we go to inject. And then kind of the final thing here, and this is what I'm going to step over there and talk about really quickly, the topic I wanted to get into a little bit was response time. So we talk a lot about speeds and pressures in this industry, which is obviously very important, but what we think at Sodick here is more important is how fast we get to that set speed, or how fast we get from set speed to 0, slow down and start to pack and hold. So we refer to that as response time, or how fast you're accelerating and decelerating. Now the advantage here, and I'm sure Mark's going to talk more about linear motors, this is a linear motor driven plunger. So essentially, you're telling this plunger to go from X to Y, and you're gonna do that every single time, but you're gonna do that at set speed for that entire stroke. So that's what I mean by response time, is really how fast we get to that set speed and the kind of the control of moving of a light plunger versus a bigger, heavier screw. So if I got a few minutes, I got a couple more things over here. Sorry, moving around a bit. So this is just kind of a comparison, right? When I talk response time, it's always nice to have numbers, but what we're showing here is a linear motor. That's, again, our V-line system. But our standard machine, which is this GL line up here, is going to be around 15 to 20 millisecond response time. If you compare that to traditional, really a lot of the machines on the market, great machines, but as far as response time, this is kind of the range that they play in. So when you get into some thin wall molding and micro molding and things like that, that's where that really becomes important, which is why we have what we call our LP model, which is a second linear valve in terms of that positioning of that plunger. So now you've increased that response time even further to 2 to 3 milliseconds. Could be up to 5, depends on the size of that plunger, essentially. So, and this is kind of what that looks like graphically, right? So basically you're looking at here, typically, I guess, Japanese right to left, but typically you might be in that 30 to 50 millisecond response time. So say your ejection speed is 500 millimeters per second, right? This is what that might look like in very basic form in terms of accelerating to that set speed. Now you're there, if you're lucky, say 30 milliseconds, you're there for a third of your stroke. Now you got to slow down and build your cushion. And so you kind of have this ramp up period. Now you're really in control of resin movement at set speed where you want to be the whole stroke. It just takes you a while to get there. Now you've got to slow down and build your cushion. So the red here, and again, this is 5. We're actually closer to 2 to 3 millisecond response time. But the red here is kind of just to show what that acceleration does. So, say maybe you have a living hinge on your part, and you want to fast fill through that portion, a real thin wall, and then you maybe want to slow down. You could, with this type of response time, you could kind of make a little step function here and, tailor that process specific to where you're at in fill with any given part. So, in molding, I think we always you want to blame the tool, or you want to blame the material, you want to blame the machine. Of course, these things have to work together, but I think a lot of times the process control on the machine side gets lost a little bit, and that's kind of what we wanted to talk about today. So I think that's kind of what I have here today. I'm going to hand you guys over to Mark Golick. Obviously, we partnered on this new booth here together, and he'll walk you through some things on the additive machinery side for us.
How's everyone doing today? Just want to welcome everyone to the booth. Want to thank Plastics Technology for giving us the opportunity to really showcase kind of in tandem how Sodick Opm and Sodick Plastic have the ability to work together and really showcase our capabilities in each of our industries. So as we were saying, we are Sodick Inc., and we are more on the EDM side of things. We're known as a worldwide EDM OEM, but we also do have an extensive line of high precision, high speed mills, and also 3D printers. What we'll be talking about today is one of our line of our hybrid printers. It's an OPM 250. This size tells you that you have a 250 millimeter cubed work envelope. What makes this machine stand out is that you have the ability to machine and grow at the same time. Biggest benefit that we see, especially working with Plustek and Flowcon, which we've created this core cavity here, is that you're able to incorporate 3D conformal cooling into your builds now. So that's going to help reduce a lot of cycle time, help with a lot of that money management and stuff. So for this example, what we do, our process that we usually go about is we load a model within in our software, create a sintering process per our conditions or per what the customer is looking for, which that's going to tell you what kind of density you're really looking to achieve within that part. Once that's created, we go ahead and we set up our cutting process. What kind of tool paths we're looking to get. From there, we select the correct tooling that we need to make sure that we achieve the right dimension, the right tolerances for that part. Once that part is finished, completed, printed, you're able to take it off the machine, do a secondary operation by either an EDM process or that take that part on, you're able to put that in your mud base and go ahead and get that right into your plastic injection press. That's about the gist of it. If anyone has any questions, we have a whole bunch of samples here of different parts and stuff that we've built here over the past year, and here to answer any type of questions you guys may have.